Hello, welcome back to Decaf-Math, and welcome if you are new here. Today I printed out a few sheets with graphs on them, and I thought that we could go over these pages, and they each represent different types of transformations of graphs of functions, and this might be useful for both algebra and Precalculus, and maybe other classes too. But we are going to focus on transformations on graphs, even though there are other contexts, okay, and other types of transformations. But I want to take an algebraic approach. So, for this first transformation, you can see that we start with this. So this is the graph of 1, 2, 3, 4, 5 different functions. So it's 5 different functions on one x, y coordinate plane. So x and y. And notice that the origin would then be right there where the x and the y intersect. So right there. And my basic function is this one that I've highlighted. Y equals x squared. Right there. The one that touches this origin. And if you've studied this before, this little U-ish shape thing is called a parabola. But really, this function could be anything. Okay? But for now, we're going to look at this U shape. And the first transformation is about just taking this U and shifting the whole thing up or down. And you might go, wait a minute, why do these kind of look like they have the same shape, but this one's kind of shorter? And why is this one longer? Well, that's just because we have a margin here and it gets cut off. So really, if we extend this, it keeps going off the page. And so you can extend any of these to all be the same length, but you can also extend any of them off to infinity. Okay? So they actually are exactly the same shape. The only difference is that I'm taking this original function and I'm moving it vertically up or vertically down, meaning taking every single point on this thing and shifting it down a set distance or up a set distance. So the y equals x squared here is called the parent function. Parent function, which just means basically it's the basic function. I'm not moving it anywhere. I'm not scaling it anyway. It's just my basic function. You won't have coefficients. You know, it kind of is a bunch of ones and zeros, pretty much. So you can substitute this with y equals x cubed, y equals square root of x, y equals sine x when you learn about trig functions. So really just your basic function, your basic version of a function, so to speak. Okay? So everything else, our transformations, are going to be relative to that parent function. So notice in this case, it's the one that goes through 0, 0, and the width, so to speak, but the narrowness or the wideness, if that's even a word, is the standard is 1. And you can show yourself that by writing out the standard form for a parabola, right? So for this type of transformation, moving it up or down, all you do is take whatever your parent function was and add a number. So x squared, in this particular case, x squared plus some constant, let's say c. So your new function, your new sort of transformed function, y new equals x squared, but I guess I'll try and generalize that. So y old plus c, meaning in this case, x squared plus c. Okay, and so if c is greater than 0, then you are shifting it up, and if c is less than 0, meaning x squared plus -1, which is x squared minus 1, right? That means down. So for example, x squared plus 4 is y equals x squared, but shifted up 4. Okay, so y equals x squared plus 4 is y equals x squared but shifted up 4, meaning every single point gets moved up 4. So that would be this from this up 4 is this. And then y equals x squared minus 2 is shifted down 2. So when you talk about shifts up or down, you have to be clear with relative to what, right? And in this case, we are talking about relative to the parent function. So shifting down 2 is this whole graph shifted down. Okay? And just kind of intuitively, you can think about whether some sort of transformation like this, adding c, if that affects your x or your y values. So remember, for functions, to graph a function, we are finding inputs. So we give an input, and our function tells us what to do with that input. So in this case, squaring it to get an output. And we pair the inputs and the outputs together as ordered pairs, right? And then we plot those points and kind of connect all the little dots to get a general shape. So what was, if for instance I have y equals x squared, 1 comma 1 would be on this graph, because if I have an input of 1, my y is 1 squared. So 1 squared is 1. And so is 2 comma 2 squared is 4. So 1 comma 1, 2 comma whoosh, 4 right there on my original. But if I have a new function, say y equals x squared plus 3, then now what was 1 comma 1, an input of 1 and an output of 1, I now have an input of 1 comma, and then I have my 1 squared, which was 1, but I'm also adding 3. So it's almost like this 1 plus a 3, meaning 1 comma 4, right? So what was 1 comma 1 is now 1 comma 4, like the equivalent, right? So what I did was I shifted the y value up 3 larger for the same x. And so it would be 2 comma 2 squared is 4, which is what we did before, but now we're adding another 3, so that's 7. So now this is 3 more. So every single point that we pick will have that outcome. The y value is 3 more, and that's kind of why we shift the entire graph up 3 when we add 3. And I wanted to take the time to kind of start this line of thinking, because this will be helpful for some of our other transformations as well. So thinking about if we are affecting the y values, which have to do with up and down, or x values, which would affect left and right. Okay? And we will come back and talk more about plotting graphs if this part kind of lost you. Don't worry at all. We've talked about plotting points on the xy plane here, but we haven't really discussed graphing yet. But we can and we will, and we can also come back to this stuff more in the future too. I'm just starting the conversation. Okay, so the first one is so I'll generalize the x squared plus c. You can do it like this. The y new is y old plus c. You can write that also. Remember, y is a function of x, so sometimes it's written like that, and sometimes you'll see like f of x equals well, okay, so I'm going to put f star, because if I do an f prime, people might think that that's the derivative. So f star is like the new transformed one, and f of x plus c. So this is about up or down. Okay? Coolio. Alright, so this is a bunch of ups and downs. So, good job. Now, as you might have guessed, we are going to go left and right. So here is our lovely y equals x squared again. Y equals x squared. That's our original parent function again. But now we are moving it left and right. Right? So these are 2, 3, 4, and 5 functions. So here's our origin. This is our parent function that we're doing everything relative to. But now we are shifting it right and left. So I'll just start with the rule, which is f of x minus c, like that, if c is positive, c greater than 0, shifts the graph right, shifts f of x right c units. Okay, so this notation is if y is f of x, okay, meaning f of x minus c for this particular case where our function is x squared would look something like x minus 1 squared. That's what this x minus c thing, f of x minus c notation means. Okay, so basically we are replacing the entire x with an x minus some number. Okay, so in the last case we took the entire function, the x squared, and we added or subtracted a number. In this case, we are replacing the entire x without the squared part, just the x, with an x minus 1 or an x plus 3, like that. Okay. Okay, so that would be the same thing for a different parent function. Say y equals sine x, y equals sine x minus 5, shifts the entire sine curve to the right 5 units. And the x plus c shifts it left. And one way to think of it is that having x minus c in general shifts the whole thing to the right, but if you have like an x plus 3, that's like x minus minus 3, right? That's the same thing, because it's like a little -1, and -1 times -3 is +3, right? So it's almost like shifting it right -3 units. Kind of a weird way of thinking of it, but it's moving it left 3. If that helps you, that's one way to think of it. If that's just really weird to you, it's easier to just remember if you have a -1, you're shifting right, and if you have a +3, you're shifting left. Okay, so if you have this, according to this rule here, f of x plus c, and remember in this little notation, this is only for c greater than 0, shifts f of x left c units. Okay, and one way to think of it here is that what was 1, 1 or 2, 4, which we already calculated in the first transformation, right? These are points on this y equals x squared. But if we were to think about having y equals, let's say, x plus 3 squared, in order to get this thing to be 1, so that we have the 1 squared, I need x plus 3 to equal 1. And if we do a little bit of algebra there, that's actually negative 2, comma 1. Right? So negative 2 plus 3 would be 1, and then we're back to our 1 squared. So basically, to get that same y value of 1, I had to move my x value left 3 so that I could add 3 to that to get my original x. So if I have a negative 2, which is my 1, moved left 3 times, so 1, 0, negative 1, negative 2, then when I plug in negative 2 into my new transformed function, I plus 3 first, so back to 1, and then I can get the same y value. So basically, in order for me to get the equivalent of my original x of just an arbitrary point, so we could do the same thing for 2, 4, in order for me to get the equivalent of that original x value that matches up with the same y, I have to subtract 3 so that when I add 3, I go back to that point. I like to think of it that way because it can be confusing with minus or plus whether you're going left or right. So that is why you kind of want to compensate for the plus 3 by shifting left minus 3. Okay, so the equivalent of 1, 1 is now negative 2, 1, and I actually don't have the x plus 3 case. Here's the x plus 2 case, is this shifted 2 over. So what was 1, 1 is now negative 1, 1. Okay, so that's how I like to think about it. Or like y equals x minus 5 squared. That is, x minus 5 squared. That is my y equals x squared graph, but shifted to the right 5 because I am replacing the entire x with an x minus 5. Okay, so that just means I need to increase every value of x by 5 so that when I minus 5, the x plus 5 minus 5 kind of gives me the equivalent of my original x. And to increase by 5 in the x means to shift it to the right or the left, right? Increasing by 5 means to the right. But this is how we adjust left and right. So now comparing side by side, our up and down, the plus c means up and the minus c, assuming that c is positive, but means down. So you can either write this or you can write it the equivalent with this c notation. C is just a constant, so as long as you define your the domain, as long as you define how you're defining c, then and you're consistent, and that's okay. So in this case, if you add a number, you go up, and that's literally because you're taking the entire function and adding the value directly. So positive would just be up and negative would be down. Okay, but for left and right, since you are adjusting the x value, it's kind of the opposite. So if you do x minus 5, for instance, squared, then you're shifting right. And if it's x plus 5, you're actually shifting left compared to your original. So x plus 5 squared. Okay? And you can do more practice with this too. Alrighty. So the next transformation is kind of harder to visualize with this particular example with the y equals x squared, but it's okay. This is about when we multiply by a number in front. So if I take my entire function, so again, we have to be clear if we are adjusting x values or if we are adjusting y values. So if I take this entire function and I do c times f of x, so again, y is my function of x, f of x equals y equals x squared. If I multiply by a constant in front, I'm basically sort of changing the y values by a scale, right, by a number. So before with the y equals f of x plus c, I am adding a number to every y value, remember? So this is for every y value. Now we are just multiplying every y value by c. So this is a situation where we're changing things in y. So again, we have our y equals x squared, our basic function, our parent function. And you can see here, this is kind of funny, it goes upside down too, we'll talk about that. But assuming that, let's look at c being greater than 0 first. Okay, so c is a positive number, let's say 2 times f of x, and in this case 2x squared. Okay, so the graph of y equals 2x squared. So basically we already, let's go back to our handy 1, 1, 2, 4. These are points on this graph. Now on the new graph, what was an input of 1? So I'm going to input 1 into my new graph. I still have my 1 squared, so that's still 1, but then I'm also going to multiply that by 2. So what was the equivalent of 1, 1 is now 1, 2. Where is this? 1, 1 is now 1, actually this is probably 3 times because I have a 1, 3 right here compared to 1, 1. Okay, I actually don't have the equations written here, but that's what I would think. Okay, so that would be y equals 3x squared, for instance. And so 2, 4, what was 2, 4 is now here. If I plug in 2, I have my 2 squared, which is 4, but then I'm going to multiply that by 2. So 8. So the y values go much faster, right? You're multiplying everything by 2. So 2 times as much for the same x. So keeping that for every point, so instead of 2, 4, I now have 2, 8. It kind of squishes this whole thing to be more narrow, right? So you can kind of think about that as kind of smushing it in more narrow, but it increases faster, right? Faster. As opposed to, so this is for c greater than 0, but also c greater than 1 specifically. But if c is still positive, but c is between 1 and 0, then that would be for instance, y equals 1/3 x squared. The same line of, same line of thinking, but our 1 comma 1 would now be 1 comma 1/3. We're kind of smushing it smaller, I guess, if you want to think of it like that, but we're taking the y values and making it 1/3 as much. So 1 is now 1 comma 1/3, right? So for everything, you just look at this line here at x equals 1. This is our original, so that's just at 1. But if we multiply by a number that is bigger than 1, say 3, we go up here. So our graph just goes more narrow. And if we multiply by something that's between 0 and 1, it's just wider, right? So that's it. It's kind of like about stretching and compressing. So then for c less than 0, it just flips it the other way around, but the same line of thinking of if it's narrow or if it's wider. But if c is less than 0, so if I have y equals negative x squared, so that's like a negative 1, I just flip it upside down. Right? Or this one would be the equivalent of this one. This, right? Because every 1 comma 1 would now be 1 comma negative 1, literally flipping it across the x. And so then y equals negative 5x squared. You can combine what we did for positive and the negative 1 situation by flipping it upside down and making it more narrow, right? So that's pretty much it. So take a look at this. This is for if we multiply by some constant in the front. But this is a situation where we are manipulating the y, the entire f of x. So in this case it's cx squared, but this also applies for, let's say we want to do, 5 times cosine of x, right? We are just taking the y values and multiplying by 5. Okay. So for this last one, this is for f of cx, okay? So it's actually easier to see this on a trig function as opposed to y equals x squared. And the reason for that is because this is multiplying, like replacing the entire x part by something times the constant. So instead of 3x squared, I would be replacing the x by like a 3x, for instance. But the weird thing about that in the y equals x squared as a parent function case is you can use algebra here to make it 9x squared. And so that's like our situation where we multiply by a constant in front. So it's kind of hard to visualize what's actually happening. It's a little weird. So instead, just coincidentally, like pictorially, it wouldn't really highlight what we're talking about. But instead I graphed y equals sine x. So our parent function is y equals sine x. And if I pick, instead then replacing the entire x part with, say, y equals sine 2x. Okay, so this is where c would be greater than 1, because now it's 2. That is the same line of thinking about shifting right or left, except in this case we are thinking about compensating for the change in x for the equivalent of our original value. So for instance, let's see, what's a point on sine x? Let's say we have pi over 2 and sine of pi over 2 is 1. So the equivalent, the parallel for this point, in order for me to get that same 1 and that same, like the equivalent of the pi over 2, I have to divide by 2. So for the new function, it would be pi over 2 divided by 2, which is pi over 4, and pi over 4 comma 1. So that if I do pi over 4 times 2, then I get my pi over 2, and I already know that sine of pi over 2 is 1. So basically, I am smushing everything. It's almost like x moving twice as fast. So I'm taking this and I'm smushing it. So it was pi over 2 comma 1, which was here. I now have a pi over 4 comma 1. Does that make sense? And so what was a pi, sine pi is 0, so what was pi comma 0 is now pi over 2 comma 0, because pi over 2 times 2 is pi. So it's compressing my function. So instead of lu, it's do. And so as you might imagine, if c is less than 1 but still greater than 0, it expands it out because it's kind of moving x kind of slower compared to our parent function. Okay, so for instance, sine of 1/3 x. So here we need, in order to match up with our, let's say pi comma 0, I actually need 3 pi. So that 3 pi divided by 3 is pi 0. So I'm taking what was pi comma 0, and now the first time that hits another 0 is actually 3 pi. So it kind of goes, whoa, I'm stretching this point out to, or not this point out, sorry, this point, because I'm comparing to my y equals sine x, and going, whoa, I need that. Except in this case, I think it's just 2 times, so sine half x, but I'm stretching it, and then for the do, it's compressing it. Does that make sense? I hope that's making sense. Getting a little bit rambly, but hopefully if you're listening to this for sleep, that you are asleep. But I just wanted to share some thoughts here, and we can kind of keep analyzing this. Maybe it would be really neat to write out like a table in the future for like a simpler parent function, and just draw all the parallels so that we can see these patterns. But just thinking out loud right now, we're not like trying to just memorize, but if you kind of want to understand transformations, it's really, are we affecting X or are we affecting Y for these kinds of the transformations for graphs of functions. So are we shifting things up or down? Are we scaling it up or down? Like, are we compressing it this way or stretching it out this way? Or are we shifting it right and left? Or are we smushing the whole graph this way or extending that way? Okay. And of course, you can combine this with studying parabolas in general, right? With our a times x minus h squared plus k stuff, because we can analyze how a goes and where this vertex goes, this h comma k. And you can also combine that with trig work, where we talk about the period of the sine function as well as the number that affects our amplitude, right, our a, and also if we shift it up or down. So this work is kind of applied in both algebra and precalculus, which is kind of why I don't want to memorize too much right now. I just kind of wanted to build some of the foundation with the algebra that we've kind of already talked about here. Okay, la-di-da-di-da, sending you all my love. I hope that this was helpful, and stay tuned for some more math soon. Bye!